Hello, welcome. In this lecture, we will talk about functions of several variables. In particular, functions of 2 or 3 variables. Let's begin our discussion with an example of a function of 2 variables. The volume of a circular cylinder depends on its radius r and its height h. In fact, we know that the volume is equal to pi r squared h. We say that v is a function of r and h, and we write v of r comma h equals to pi r squared h. Definition. Let D be a subset of R2 space. A function f of 2 variables is a rule that assigns to each ordered pair of real numbers x comma y in the set D a unique real number denoted by f of x comma y. The set D is the domain of the function f, and its range is the set of values that f takes on. That is, the range of f, denoted by this symbol, is a set of all outputs such that the input, the ordered pair x comma y, is in the domain D. We often write z equals to f of x comma y to make explicit the value taken on by the function f at the general point x comma y in the domain. The variables x and y are independent variables, and z is the dependent variable. A function of 2 variables is just a function whose domain is a subset of R2 space and whose range is a subset of R. It's often called a real valued function. Let's see an example. For each of the following functions, find and sketch the domain. Let's have a look at the solution. The expression for f makes sense if the denominator, x minus 1, is not 0, and the quantity under the square root sign, x plus y plus 1, is non-negative. So the domain of the function f is the set D is a set of all ordered pairs in R2 space such that x plus y plus 1 is greater than or equal to 0 and x is not equal to 1. The inequality x plus y plus 1 greater than or equals to 0, or can be written y is greater than or equal to negative x minus 1, describes the points that lie on or above the line given by the equation y equals minus x minus 1, while x is not equal to 1. Means that points on the line x equals 1, a line parallel to the y-axis, must be excluded from the domain. as shown in the figure. So, the shaded part of the xy plane is the domain of f, excluding the points on the dotted line given by the equation x equals 1. To find the domain in the question B, we see that the natural log of y squared minus x is defined only when y squared minus x is strictly a positive real number. That is, y squared is greater than x. The domain of f is the set D of all ordered pairs x comma y in R2 space such that y squared is greater than x. This is the set of points to the left of the parabola defined by the equation y squared equals x, as shown in the following figure. Let's have a look at another example. Find the domain and range of the function g defined by the equation g of x comma y is defined to be equal to the positive square root of 9 minus x squared minus y squared. The domain of G is the set D of all ordered pairs from R2 space such that x squared plus y squared is smaller or up to equal to 9. Since the quantity here has to be non-negative, this gives this inequality. The set D is called a disk with center 0, 0 and radius 3, as shown in the figure. The range of G is the set of all real numbers z such that z equals to the positive square root of the quantity 9 minus x squared minus y squared, where the pair x comma y is in the domain D. Since z is a positive square root, then it has to be something non-negative. Also, because x squared plus y squared is smaller than or equal to 9, we have z must be greater than or equal to 0, but smaller than or up to equal to 9. So the range of the function g can also be written in the following way. Or as in the notation of a closed and bounded interval. Definition. If f is a function of two variables with domain D, then the graph of f is a set of all points x comma y comma z in R3 space such that z is given by f of x comma y, where x comma y, the ordered pair, is in the domain of the function f. example, the graph of the function g defined by this equation is the set of all ordered triples x comma y comma z in R3 space such that z is given by g of x comma y, which is also equal to the positive square root of 9 minus x squared minus y squared, where the pair x comma y is in the domain of the function g. The level curves of a function f of two variables are the curves with equations f of x comma y equals to k, where k is a constant in the range of the function f. A level curve f of x comma y equals to k is the set of all points in the domain of f at which f takes on a given value k. That is, it is the set of all ordered pairs in the domain such that f of x comma y equals to k. In other words, it shows where the graph of f has height k, as shown in the following figure. Example: sketch the level curves of the function g where g of x comma y is defined to be equal to the square root of the quantity 9 minus x squared minus y squared for k equals to 0, 1, 2, 3. So we want to plot the level curves of the function g where g of x comma y equals to 0, g of x comma y equals to 1, and so on. Let's have a look at the solution. The level curves are given by this equation: g of x comma y equals to k, or the positive square root of the quantity 9 minus x squared minus y squared equals to k. This can be rewritten by squaring both sides in the following form: x squared plus y squared equals to the quantity 9 minus k squared. This is the family of concentric circles with center at 0, 0 and radius the positive square root of the quantity 9 minus k squared. Let's try to plot the level curves in the following applets. So the half sphere we see here is the graph of the function g of x comma y equals to square root of the quantity 9 minus x squared minus y squared. And the domain is shown in the xy plane, or we see in this figure, which is a disk, the set of all points inside and on the boundary, defined by the equation x squared plus y squared is smaller or up to equal to 9. Now, if we set the k value 0, we get in fact this circle as a level curve. Now for the next k value, k equals 1, we get another circle. This level curve is obtained by intersecting the sphere by the plane z equals 1. And we see that the intersection is this circle, which is parallel to the xy plane, but at height 1, z equals 1. So along every point here, along this curve, every point, the z value is equal to 1. If we project this circle onto the xy plane, we get the circle inside the bigger one, and we can also see the circle here, the inner one. Similarly, for the next k value, we have another level curve. At every point on this curve, the z value is 2. If we project this onto the xy plane, we see the level curve there, or the level curve here. Similarly, if we set k value equals to 3, we get the equation x squared plus y squared equals to the square root of 9 minus 3 squared, which is equal to 0. Therefore, the plane z equals to 3 intersects the sphere at one point only, at the top here, whose coordinates are given by 0, 0, 3. If we project this point onto the xy plane, we get the point here, 0, 0. So these are few level curves of the sphere: 0, 1, 2, and 3. Similarly, a function of 3 variables, f, is a rule that assigns to each ordered triple x, y, z in a domain D, now a subset of R3 space, a unique real number denoted by f of x, y, z. For instance, the temperature T at a point on the surface of the Earth depends on the longitude x and latitude y of the point and on the time t. So we could write t equal to the function f of x, y, t. Let's have a look at an example. Find the domain of f if f of x, y, z is equal to the natural log of the quantity z minus y plus x times y times sine of z. The expression for f of x, y, z is defined as long as the quantity in the natural log z minus y is strictly positive, since natural log is defined for the strictly positive real numbers. So the domain of f is the set D of all ordered triples in R3 space such that the z coordinate minus the y coordinate is greater than 0. This is a half space consisting of all points that lie above the plane given by the equation z equals to y, as shown in the following figure. So the half space is given by the equation z equals y, and the domain of the function f is the set of all points that lie above, strictly above, the plane given by the equation z equals to y, as shaded roughly here. It is very difficult to visualize a function f of 3 variables by its graph, since that would lie in a 4-dimensional space. However, we do gain some insight into f by examining its level surfaces, which are the surfaces with equations f of x comma y comma z equals to k, where k is a constant. If the point x comma y comma z moves along a level surface, the value of the function f at x comma y comma z remains fixed. So level surfaces are a 3-dimensional version of the 2-dimensional level curves. Let's have a look at an example. Find the level surfaces of the function f at x comma y comma z is defined to be equal to x squared plus y squared plus z squared. The level surfaces are given by the equation x squared plus y squared plus z squared is said to be equal to k, where k is some positive real number. This forms a family of concentric spheres with radius the square root of k. Thus, as x comma y comma z varies over any sphere with center at the origin, the value of f at x comma y comma z remains fixed. Let's have a look at an animation. In this animation, we will plot the level surfaces of the function f, which was defined to be equal to x squared plus y squared plus z squared. So the level surfaces are given by the equation x squared plus y squared plus z squared is equal to k. In the first case, let's set k equals to 0. So we easily recognize that the equation x squared plus y squared plus z squared equals to 0 is just a point, the origin, as shown in the violet color here. Now for different value of k, let's see. We see for different values of k, we are getting the larger and larger spheres. Each of these spheres is a level surface of the function f. These are few members of this family of level surface.